Today I'll be talking about expected value and variance. So expected value is just an integral on the probability space. Okay, so we can talk about the more probabilistic meaning in a second, but let's start from the viewpoint of analysis. So for a measurable random variable, and remember we said a measurable random variable, what is that? Okay, and actually measurable is kind of redundant here. For a random variable on our probability space, what's a random variable? That's a measurable function on our probability space. Okay. So for a random variable, define expected value, let's say for x, a random variable. We'll define the expected value of x, this ex, as the integral of x on the probability space. So we're integrating on the probability space with respect to the probability measure. And remember that we're suppressing a lot of notation here. This is the same thing as this, right? We're just starting that practice of suppressing notation in probability that we see a lot. Okay. So the expected value of x, some random variable x, okay, is just the integral of x on the probability space. All right, so nothing too complicated about that. When the integral is well defined. Okay, so let's recall what it means for an integral to be well defined on a probability space. When we have a measurable function, we can define these positive and negative integrals, right? The integral of the positive part of x and the integral of the negative part of x, okay? And this integral, the integral will be defined if this difference is defined, right? So at least one of these has to be finite, okay? We could have infinity minus some finite number, or we could have some finite number minus infinity. Those are both defined in the extended real numbers, but we can't have infinity minus infinity. Okay. So we have the expected value or expectation of x is defined when the integral is defined. Okay. So from the analysis viewpoint, as I said, this expected value of x, this e to the x, is just an integral of some measurable function on a measure space. Okay, and it just so happens that the measure space we're dealing with is this probability space that is encapsulating these, random occurrences, perhaps. Okay, so now what's an interpretation of the expected value? Okay, if you want to put some kind of real world meaning to it, it's a weighted average of these functional values of the random variable x. So it's kind of like the average of the values of x, but it's weighted by the probability, right? If you kind of go up here to our statement of what the expected value is, think of it as like, all right, we have a functional value here and we're multiplying it by that probability and we're adding all those up, and that since the total measure of the space is 1, it kind of gives us an average value, right? But the higher the probability, the more weight we place on that functional value, right? So we have this idea of a weighted average of the functional values. However, as my advisor would say, there's nothing expected about expected value, okay? So there's this kind of connotation with the term expected that, okay, that it's like the most likely value, but that's not really true at all, is it? If, for example, we consider rolling a die, okay? So let's roll a fair die and consider, let's let x be just the face value of the die, okay? Okay. What would this integral be, this integral of x on our probability space? Well, we haven't really proven this yet, but maybe intuitively know, okay, the functional value 1 has probability 1/6. Functional value 2 has probability 1/6, and so on. And the integral is just the sum of these terms, okay, which is equal to 1/6 times that sum. And it really just simplifies to 7/2, okay, which is 3.5, right? So the expected value of this die roll is 3.5, but we would never expect to see 3.5 come up, right? We would never roll a die and say, oh, to ourselves, we would never say, we would never say to ourselves, oh yeah, the expected value is 3.5, so I'm probably going to see a 3.5 on that die, right? No. So it's really just an average, and we have to keep that in mind, that it's just an average, kind of average of these functional values, a weighted average, and we have to be careful what kind of conclusions we draw from that value. We have all the since the expected value is just a integral, we have all the tools from analysis and a lot of the terminology from analysis. So for example, if the expected value of x is finite, we say expected value of absolute value of x is finite, we say x is integrable, okay? Just like with a function on some measure space, right? If we have some function and the integral of the absolute value of the function with respect to that measure, let's call it, if that's finite, we say f is integrable, right? So just analysis terminology. Quick note about notation. When we have expected value, a lot of times I like putting the brackets, but a lot of times these brackets are omitted. Okay, so you might see something like this for expected value of x, and expected value of absolute value of x. Some people would write, absolute value inside the brackets, but a lot of times that's just omitted, and you just have this. Okay, they're, these are the same, these are the same. Okay, so again, some suppressed notation, which you've seen me apply here. So the properties of this expected value, the expectation, these just follow over from integration, right? The expected value is an integral, so it has all the properties of integrals, right? It has linearity. So expected value of, let's say x is a random variable, okay? Expected value of a times x plus b is what? A expected value of x plus b, okay? You can try this on your own if you need to convert it to an integral, okay? Try that on your own. And then remember that the measure of the space is 1, right? So when we split off this b, it's going to be b times 1, which is just b. Okay. And then from integration, we also have our convergence theorems, right? Our kind of big measure theoretic convergence theorems like monotone convergence theorem, Fatot's lemma, Lebesgue-dominated convergence theorem, etc. Bounded convergence theorem, things like that. So we have all these nice theorems from measure theory and real analysis, and we're going to see some nice inequalities carry over as well, and I'll kind of detail those inequalities later. Okay, continuing. We have a nice little proposition here. And this is extremely powerful. It relates integration on the probability space to integration on the real line when x is a real valued random variable. Okay, so recall in the previous video, I had this little graphic where it was the probability space, and then if we have a random variable on our probability space, this kind of induces a measure on R, and we can think about the measure, the distribution, which is just a probability measure induced on R. And we could carry that a step further to, if we have a density function, okay, integration with respect to the Lebesgue measure. Okay. So this is this proposition is the first step in doing something similar or doing the same thing for expectation, right? And so instead of integrating on the probability space to find expectation, we could just integrate on R with respect to this distribution, or we could even take it a step further and integrate on R with respect to the Lebesgue measure to find expected value. So let's go through the proposition. Let X be a real valued random variable and H a real valued function from R to R. If H of X is greater than or equal to 0, or H of X is integrable, so the integral of the absolute value on the probability space is less than infinity, then we have this equality here. The integral of H of X, this is capital X, our random variable, on the probability space, that is going to be equal to H of X, where this is lowercase x, just the independent variable X. It's going to, we can integrate H of little x with respect to this distribution on R and get the same value, the expected value. Okay. And this is a good, I wrote this proof out. It's a little long because it shows a really common technique. And this is really it's a real analysis technique. If you want to show something if you want to show, I guess the general layout is, if you want to show something, you want to show a property for like an integral, that the integral of some class of functions has some property. So let's say f of x, dx. Okay. And let's say you want to show it equals something for all integrable functions. Okay. How would you do that? How can you show something that's so general? As general meaning like applied to it's true for all integrable functions. Well, you first show it for indicators, and I've kind of written this out here. You first show it for indicator functions, right? And then you show it for simple functions, which are just linear combinations of these indicator functions. And then you show it for non-negative functions. And then you can show it for integrable functions. So we have this nice progression. Okay. So we'll try and show this property here in this sequence. We're going to show it's for indicator functions and simple functions and non-negative and integrable functions. Okay. So let's start with indicator functions. So let's assume our function h is an indicator function for some set A in the Borel sigma algebra of R. A note, I usually am writing Borel sigma algebra of R, but really we could probably just do the Borel sigma algebra on the extended real numbers, right? So we allow infinity and all that for more generality. It all carries over. So if I write Borel sigma algebra of R, think of this as including the extended real numbers, the infinities. Okay. So we're assuming h is this indicator variable. In this left side, this left and right side is the same thing. This is just with the suppressed notation. Okay. And then when I was starting probability, the suppressed notation really threw me. So I figured I would kind of write out some of the full notation as well. So that's the same thing. Okay. So let's go over here to this suppressed notation. All right. So I want to integrate. Let's start integrating this let's integrate h of x on our probability space. Well, h is just an indicator function, right? So let's just rewrite that as 1 sub a of x. And then what is this 1 sub a? This this is, you know, even though it's a composition of functions, this is still going to be this is going to be an indicator function, right? This is going to have value 1 when x is in, or excuse me, when omega is in what? X inverse of a, meaning when x of omega is in a. Okay, this function will have value 1. Okay, so what is this? This is an indicator function. This is an indicator function for some set in the Borel-Segner algebra on omega. Okay, so some set in F. And really, it's going to be the set x is in A. Okay, so really what this integral gives us is the probability that x is in A. And from last video, when we were constructing the distributions, right, we know that this is going to be the distribution, the measure on our real line induced by our random variable x. Okay, so really what we have is the measure of A, okay, with respect to this distribution here. Okay, and then on the right side, maybe we see a bit more, maybe it's a bit clearer if you're used to that notation. Okay, just writing, basically just keeping track of the omegas. Okay, so when we're integrating on this probability space, we have h of x of omega. Again, we have the same interpretation. Okay, we're replacing h with, okay, h is an indicator function, so we just write that. Okay, and then this thing, this is also an indicator function. It's going to be, and then it's a indicator function for this set here. Okay, all the omegas such that x of omega is in A. Okay, which is if really just the pre-image of A in terms of x, right? Which is again our viewpoint of the distribution. Okay, so on one hand, we've shown that this integral, focus on this left side, this integral on the probability space is equal to the distribution of A. Okay. On the other hand, let's now consider the equation from the other side. What's this integral? Okay, so I'm integrating h of little x with respect to this measure here. Okay, well, we're still saying h is an indicator function. Okay, so h is equal to 1a of little x. Okay, and what is that? Think of just in terms of analysis. Okay, what is the integral of an indicator function? Okay, with respect to a measure, that's just the measure of that set, right? So we have this. Okay, so on the one hand, this equals mu x of A, and on the other hand, this equals mu x of A. So then this must equal this. Okay, so we've shown it for this indicator function. But by the linearity of integration, the same thing is going to hold when h is a linear combination of these indicators, right? In other words, a simple function. Okay, so it's true for simple functions, just by linearity of integration. Now let's do what's the next step in our process? We've shown indicator, boom, we've shown simple. Now we want to show non-negative. Okay, so let's assume h of x, h of our random variable is non-negative. Okay, then think about the positive part of h of x. Okay, if h of x is always greater than or equal to 0, then this function here has to equal its positive part, right? Okay, so h of x equals h of x plus. Okay, and now note this, that whether we take the positive part of h of x or the positive part of h of x, they're the same. These are actually the same function. Okay. To see that, I've kind of written out here. All right. What's the value of this function? Okay. This function is going to have the value h of x if this stuff in here is positive, right? But to be positive, x has to be an h inverse of 0 to infinity, meaning this is again kind of shorthand. This is like a set omega such that x omega is in 0 to infinity. Okay. All right, so we have this. But if we think about it, this is the exact same thing, right? The positive part of h of x, well, what is that going to be? It's going to be equal to h of x, again, if x is in that same set. Okay, so these are actually equal. So instead of writing this h of x here, we can carry that to the h. Why is that important? That's going to allow us to use monotone convergence theorem. Okay, so we know h plus is a positive function, positive measurable function, non-negative measurable function. So we can say it's the limit of an increasing sequence of simple functions, right? H plus equals the limit of these HNs. Okay. In other words, and this is what, almost surely, or almost everywhere, which we call almost surely in, well, actually, we're not, H is not defined in the probability space, so let's say almost everywhere. Okay. Then by the monotone convergence theorem, what do we have? Let's consider this. Okay. So let's consider these, let's consider what these, forget about the limit for a second. Let's consider what these simple functions are equal to, the integral of these simple functions, right? So the integral of these simple functions, well, each one defined on the probability space, we've already shown for each of these, the integral is equal to this integral, right? Now let's take the limit, okay? Take the limit of everything. Let's now factor in this limit here. We have the limit on both sides, boom, limit, limit. Okay. Since these, since hn of x, this is a increasing sequence of measurable functions on R, right? So by monotone convergence theorem, we can take the limit inside the integral, okay, which I've done here. And then once it's inside the integral, what's this limit? Okay, what is this limit? Limit of hn, well, we've already said that's h plus, right? So we have the integral of h plus of little x. Okay. So we have this is equal to this. On the other hand, let's go back to that first box here. We have the limit of hn of x on the probability space. Let's take the limit inside the integral before, and let's not transform into the space R. Let's leave this on the probability space. I take the limit inside by monotone convergence theorem again. And this limit is again h plus of x, but now it's defined on the probability space, right? So basically what I've done is I've used monotone convergence twice. First, I transformed via the distributions from a probability space into my real line, okay? And then I did the same thing, just leaving it on the probability space, and I got these two equalities, okay? This box, okay, one, let's say one, we'll call this 2, okay? And on the other hand, this is the same 1, and we'll call this 3. So 3 has to equal 2, right? And 3 and 2 are kind of what we're trying to show are equal. All right. So I have the integral of this non-negative function, okay, on the real line with respect to this measure is equal to that integral on the probability space. Okay. So I've restated here what we have, and really what we're concerned with are these two. Okay. Now that's what we were trying to show, right? We've shown our result for non-negative functions now, since we had started by assuming for this step that h was a non-negative function, right? So h is equal to its positive part. So in other words, we have h of x dp. Okay, so we have our result for positive or non-negative functions. All right, what's the last step? All right, so now kind of going back up to our steps, we've shown our result for indicator, simple, non-negative, and our next step is to show our result for integrable functions. Okay, so now let's assume h of x is integrable. By the previous step, this result for non-negative functions, okay, we know this integral, the positive part of h, is equal to this. And same result holds for the negative part, right? And recall that the integral of h of x is the difference of its positive and negative parts, right? Now, we have assumed that h is integrable, h of x is integrable. So we know that one of these, actually both of these, have to be finite, right? So these are both defined, so the difference is defined. All right, so these things equal the integral, this integral here, right? The integral of h of x with respect to this measure, okay? So we've shown our result. It's just by breaking our measurable function down into positive and negative parts, and then using our previous step on these individual pieces. So we have our result, and let's just kind of rewrite our result here. Let's see, how can we rewrite that? E of h of x, where h is just some measurable function, equals, okay, let's rewrite what this is on the probability space. Okay, this is just a translation of what the expected value is. And then what we've just shown is that this is equal to this, the integral on R. Okay, why? Why do we care? So let's see an application. It gives us a convenient way to compute like numerical values for expected value. Let's let h be the identity function. So let's let h equal the, whatever you want to call it, identity function. Okay. Then, okay, expected value of, I could write identity function here, right? But it doesn't really have an effect. Okay. Okay. So expected value of x on the probability space, the integral on the probability space is going to be equal to this, okay? The integral of my independent variable x with respect to this measure, okay? So this is my result. This is a way for us to transform my expected value on a probability space to an integral on R, okay, with respect to this measure, okay? We're just integrating x. And if I can go a step further, remember if mu of x is absolutely continuous with respect to the Lebesgue measure, there's a Radon-Nikodym derivative, right? And so I can write the expected value as x times f of x, where this is that Radon-Nikodym derivative, which we call a density function. And now I'm integrating with respect to the Lebesgue measure, okay, what I'm most used to. So I have this really nice way to transform expected value from integral on a probability space, you know, kind of this weird nebulous idea, to this very, you know, concrete idea of, okay, I'm integrating on this vector space, this this space R, and I'm just integrating x times some measurable function f of x. Okay? So these are going to be very useful for practical applications. And in the previous video, I kind of made, I don't know, I felt like I made the argument that this was absolutely necessary. These transformations were absolutely necessary to work with these integrals. But that's not, I mean, in practice, maybe practical applications, yeah, you're going to be dealing with, you know, you're going to want to use these. But for theory, for proofs and all that, this integral is just as well defined, I suppose, as, you know, these two. So if we're working on proofs and we're trying to show inequalities, things like that, you know, usually we don't even transform into, you know, the real line. Okay, we just stick with the integral on the probability space. But when we want to do, you know, some practical applications, some numerical applications, maybe we'll use this theorem to transform my expected value from, you know, the probability space to my real line. Okay, so these equalities are crucial. And then we have some inequalities, some integral inequalities, and these are going to be very, very useful in theory and proofs, things like that. And these are almost all just direct carryovers from real analysis. So Cauchy-Schwarz, I have absolute value of expectation of x times y, okay, where we're assuming x and y are both in L2, meaning they're both square integral. Really, this is, you know, the Cauchy-Schwarz inequality we're used to from real analysis, or if you're not familiar with that from real analysis, you know, take it all the way back to linear algebra, right? This is just this integral, this expectation is if these functions are in L2, this is just an inner product, right? So we have this Cauchy-Schwarz inequality. And I've written absolute value of the expectation, but really, you know, we could also, you know, it also holds for expectation of the absolute value. Okay, so the inequality also holds, you know, if I want to write it like that. Okay, and since, I mean, these, like I said, are direct carryovers from analysis, so I'm not going to put the proofs here because the proofs would be the exact same as in real analysis, right? So you can look those up. So we have the Cauchy-Schwarz inequality. We have the more general version, the Holder inequality, okay, which I haven't used, you know, it's so fundamental, I guess, that people, you know, I should mention it. I haven't used it too much in probability, more in my brief studies of PDEs. I'm no expert in that field, but I know Holder inequality is used just a shit ton in PDEs. So we have the Holder inequality, the Minkowski inequality, which is great for showing these LP spaces are what that they have the triangle inequality, which makes them what norm spaces. So showing that the LP is in fact the LP norm is in fact a norm. What I would say is more important is the not more important, but something I've used a lot more than maybe Minkowski and Holder is this Chebyshev inequality or Markov inequality. I've heard it called both. So let X be a real valued random variable and phi be a positive function, a positive real valued function from R to the positive half line. Okay. And assume phi is measurable. Okay, so let A be some set in the Borel sigma algebra, and again, maybe we're doing the extended real numbers. Okay, and let M sub A be defined as this infimum. Okay, the infimum of phi of X for X in that set. Okay. Then we have this inequality here. The probability that X is in that set A is going to be less than or equal to the expected value of phi of X over M of A, M sub A. If this this infimum is greater than 0, okay, because we want this quotient to be defined, right? So this this inequality holds for all A, such that this infimum is greater than 0. Okay, and this is a simple proof, right? I have E, the expected value of phi of X. Okay, that's going to be greater than or equal to this expected value, right? Because this is just I'm integrating a positive function on a smaller set, right? So this should be larger than this. Okay. And now let's look at this guy here. Okay. Well, on the set A, what did we say about A? MA is the infimum of my phi of X values on that set, right? Okay. So this phi of X has to be greater than or equal to M of A, because this is basically the infimum of this function on that set. Okay. So this expected value has to be less than or equal to this. Okay. All right, and then this is just a constant. This MA is just a constant, so I can pull it outside. All right. And then I have integral of an indicator function. Okay, that should just give me the probability. And I don't think I mentioned that actually, but that's a super useful idea. Okay. But trust me for now that this integral, this expectation is equal to this probability. Okay. And what is this indicator variable? Indicator variable of X in A. Okay. Remember, X in A is all the omega, such that X omega is in A. Okay. So that's kind of the indicator variable we're dealing with. Okay. And this is a set in this thing's a set in F, and so I can evaluate its probability. And that really gives me my my inequality. Here I'm done, right? And then I've just restated everything here. I divide both sides by this infimum, and I get my result. Probability that X is in A is less than or equal to 1 over M of A times E, the expectation of phi of X. And we have our result. But let's revisit a tool we use. I said that the expectation of that indicator variable was just the probability of the indicator variable, right? And that's just super useful. Whenever, let's write it more generally, the expected value of this indicator function is just the probability of that set A. Okay. And this is not too complicated an idea. Think about the indicator function. We can write the notation. This is 1a of omega, little omega, right? All right. And then let's just write out what the integral would be. Okay, the expected value. It's constant on these two sets, right? So this should be equal to 1 times the probability of A, the measure of A, plus 0 times the probability of A complement, which is probability of A, plus 0, which is probability of A. Okay, this is a simple function, right? So integral of a simple function is just, the coefficient times the measure of the set. Okay. So it just comes from the idea of integrating a simple function. But it's a super useful idea to keep in mind, which we use in this step. Okay. And that really wraps up the expected value introduction. So now let's move on to variance. So more generally, if I integrate x, my random variable, to the power k, okay, so expectation of x to the k, this quantity is defined as the kth moment of x. Okay. So we're going to work with variance, which is not directly the second moment, not necessarily, but we need the second moments to calculate variance. Okay, so assume the second moment of x is finite, i.e. x is square integrable. Okay, so second moment being e of x squared. So assume this is finite. Well, if that's finite, we can define the variance of our random variable x. So let's describe it in mathematical terms, and then we'll talk about the intuitive meaning behind this. So we'll define the variance of x as this. Okay, var of x, variance of x, is the expectation of this quantity here, absolute value of x minus mu squared. The absolute value is kind of redundant, right? Okay, so this would be one definition, all right, and let's just write out an equivalent property. Okay, just yeah, I'm going to make my own confusing notation here. For what follows, what does mu mean here? Okay. So in the previous stuff, I've been using mu as the distribution of x, right? Right now, let's use the notation that mu is equal to expected value of x, just because I don't want to have to keep writing e of x. Okay, and it's going to get weird if I do e of x inside e of x. Okay, these nested expectations. So let's use this notation here, that mu is equal to expected value of x, and remember, this is just going to be a constant, right? Okay, if x is square integrable, then it's integrable, so this is some finite number. Okay, so this is defined. All right, so let's find a equivalent formulation of this variance. Okay, so we're saying variance is equal to this. This is what we've stated just now. Okay, and as I said, the absolute value is a bit redundant, so let's just get rid of the absolute value and write parentheses. Okay, and now let's square this out. Let's go ahead and square this and simplify everything. All right, I get this line. Okay, I get expected value of x squared minus 2 mu times x plus mu squared. Okay, and let's just split this up into three integrals here. Well, for this integral, I have a constant integral of mu times x, right? And I can bring that mu outside the integral, okay, which I've done here without showing. And then this is a constant, so the expected value of this is just, the expected value of that constant is just that constant, okay? And now, what's expected value of x? Well, that's, we've said up here, that's mu, right? So this minus 2 mu times expected value of x just becomes minus 2 mu squared. And then I have plus mu squared, okay? So what I have is expected value of x squared minus mu squared. And if you prefer that without the mu, okay, same thing. Expected value of x squared minus expected value of x squared. And let's go straight into properties. The variance of ax, a times x plus b, is going to be a squared times variance of x. And I'll kind of, after I kind of explain my intuitive viewpoint of variance, I'll kind of come back to this. You can see this just by, working out this calculation for yourself. The b should cancel, and this square here is going to make a, it's going to square a. Okay, so we should end up with the variance of ax plus b is just a squared variance of x. Now, to kind of understand this variance a bit better, let's think about what the variance is, what it kind of means. Maybe it's kind of clear from the name, but the variance is in some way a measure of how much our random variable deviates from our average. If you think about these bell curves, right, that we've probably all seen before. Okay, where maybe this crest is kind of representing our expected value, our average or whatever, and then all our data points are kind of clustered around this average with varying levels of probability. And the farther we go out, the less likely these events are. But really, it really depends on the underlying random variable we're talking about, right? What if our curve is more like this? What if our stuff's more spread out? Okay, this might not even be a very good graphical representation of what's going on, but we could have the same average with a lot of different spreads of data. So we need some way to quantify how spread out our functional values can be, right? So that's how I view this variance. It's this kind of deviation from the mean or the expected value. Why do we use x minus mu squared? Why don't we just use e x minus mu, right? Why don't we just use this expected value? Okay, this is the integral of the actual deviations from the mean, right? Well, we would want it to be non-negative at the very least, right? Because let's say I have this kind of symmetrical distribution about the mean. I got negative variation here, positive variation here. They cancel out, and I would get that integral is equal to 0, right? So at the very least, we want it to be non-negative. So we can't use this. Well, what about this? Well, this isn't so good either, because well, this is kind of maybe philosophical, maybe a bit beyond me at this point, but this just has better properties, especially when we start incorporating ideas like independence, uh, which I've kind of just stated here. This is kind of my cop-out answer that they expect this measure of our variance, this measure of our variation from the mean, it has better properties, and the properties it has are great. We could, once we have independence, we can say, okay, the variance of the sum of random variables that are independent is just the sum of the variance. Okay, so it's got this great property that if X and Y have a certain condition, meaning they're independent, their variances are additive. Independent. Okay, meaning var of variance of X plus Y equals variance of X plus variance of Y. Okay, which is kind of what you would hope for, right? Let's say I have two random variables and I add them together. How much is their sum going to differ from the average? Well, if they're independent, if these random variables don't influence each other too much, we would expect the variances just to be the sum, right? So that's a very nice property that we want this variance to have, and that's not the case if we use this measure of variance here. If we use this measure as our deviation from the mean, then the variance of X plus Y, we could only say it's subadditive. If we use this, then that deviation from the mean. Okay, we would have this kind of triangle inequality. This is less than or equal to all right. So we don't have the nice equality we have here. We have this subadditivity, or this, yeah, we have this inequality. Okay, so my cop-out answer would be this formulation of variance has just better properties. This measure of the deviation from the mean. And now that we have that idea, let's kind of let's talk more about the intuitive understanding of variance. This is looking at our definition of variance. Okay, this is deviations from the mean, but it's still kind of a weighted measure. This gives the greater the deviation, right? Squaring it gives it greater and greater weight. So this is really putting bias on larger deviations. Okay, so large deviations are given greater weight in our measure of distance from the mean, and that's kind of what you would. That's kind of how you would interpret this. Okay, if I'm scaling my random variable by a, then that variance should be squared. Okay, not squared, but the squared multiplied by the square of that factor there. Okay. And then if I'm shifting my random variable left or right, that's not going to really influence the variance at all, right? It's just going to move my entire kind of distribution left or right. So that's how I think about that b getting canceled out. A couple quick definitions. We've seen the variance. The square root of the variance is what we call the standard deviation of x. Okay. And then we can also define something called the covariance between two random variables, covariance of x and y. That's going to be this expectation here, x minus the expected value of x. So I'll write mu of x. I'll let mu of x equal expected value of x in this case, and mu of y, something similar. Okay. Then covariance of x and y is just this expectation here. And as you would hope, covariance of x with itself is it just becomes variance of x, which you can see if you plug that into here. Okay. So there's a lot to be said about variance. For this brief introduction, I'll stop there. And now that we have this expected value in these variants, now we can start looking at some distributions and density functions of random variables and looking at these random variables a bit in depth and kind of looking at their properties, which I think will be the next video. And we can also start doing some problems, which I'll kind of collect some problems for you guys to try if you like, and post solutions on my blog, which I believe I link to in all my videos. So I'll start posting problems and solutions like that. Hope you enjoyed it.